So I'm going to briefly talk about how we go from the problem that is driving this work to the data that powers it and the formation of decision support tools. Next slide, please. And I am going to present here a very an informal development model for decision support tools, but this work is not just mine. It is also Ankita Raturi's and Victoria Ackroyd's, Rohit Banduni's, and of course, Stephen. So, to start with our development model for cover crop decision support tools, we need to understand the problem. And a lot of this is happening in conjunction with the social science team. And so we are trying to understand the challenges that serve as barriers to entry to cover cropping and why they are problems. And as all of us are probably familiar with, that these barriers are characterized by complex semi-structured decision-making opportunities. And we're doing this in the context of agroecosystems where there is a lot of nuance and constantly changing systems. But fortunately, the solution lies in the problem, and that is that we need decision support, and there are decision support systems. And so decision support systems are designed to like theoretically designed to help organize and present information to foster decision making for problems that do require human judgment. And note that like these models, this concept, decision support tools or systems, this is not a new concept that we're bringing to the table. This is something that's been around, that started in the late 60s, but has become more accessible to a wider range of fields, with the advent of like personal computers and the World Wide Web and browsers. So decision support tools have been around for a bit, but they are quite young, especially in comparison to the field of agriculture. And so there's a lot to learn on how we bring them into this work. One of the first things to really keep in mind is that they're hard to build. And the reason is because we have to kind of check off a series of criteria in order to make like an effective decision support tool. So they need to be simple or easy to understand. They need to be robust, meaning that it should be hard to get absurd answers from, easy to control. The user should be able to get the input data in. They should be adaptive, meaning that the underlying models should be adjusted as new information is acquired, and they need to be as complete as possible. And finally, easy to communicate so that the way the user can quickly and easily change their inputs and obtain and understand their outputs. And so once we have a good understanding of our decision, so starting at the top, once we have a good understanding of our problem, we start to formulate a dictionary, a data dictionary. And if you could go to the next slide. So a data dictionary really just determines how you represent the data that is underlying this decision support flow. And so in this example, we had like, what is the role of a plant as a cover crop? But there was discussion about the economic evaluator decision support tools. And so in that case, it might be looking at the role of a cover crop with an economic lens, and that dictates how you formulate your dictionary. And next slide, please. And so in conjunction with formulating a dictionary, you need to formulate your decision flow. What is the process of our users and having to make these decisions? And you're not even and it's important to understand their entire flow for adopting the cover crops. So it's not just species selection like my particular team has been working on, or our team has been working on, but also like, what comes next? The mixes, the seeding rate calculator, economic evaluation, planting methods, weed management, determination methods, all of that needs to be understood in this model to help formulate that data dictionary, so that way it can connect with all these other potential tools. And then from there, we have data acquisition and verification, and a lot of this is already going on in PSA. And so that includes, just the on-farm trial data, also the outputs from the models developed by our PSA group that are utilizing that data. Also expert opinion, like we've been doing with the species selector. So in this acquisition, there's a lot of potential places to be acquiring that data. And then the verification aspect of that is actually assessing that data is as close to accurate as we can get it. And then moving back over to, in the parallel of this diagram, over to after the decision flow model has been settled, we have the designing of the user experience. And this is when we start to look at how are we going to present all of this information to the user so they can make the decisions they need to make. And so we start that with sketches and some paper prototypes, and then we refine it enough so that way we can create a prototype. Next slide, please. And a lot of times we'll create these high fidelity prototypes to allow ideal end users to poke around and see if this is helping with decision support, or if this provides decision support rather. And so in this case, this is an example of a high fidelity mockup we created, which is literally just images one after another in a slideshow that had hotspots for clickable buttons, but it demonstrated the concept. And once we were able to, and once any team is able to demonstrate that their prototype and that their design is effective enough, you can go into development. Next slide, please. And so here we are, second from the bottom. And then the development phase is when we're pulling in all of the decision support tools, is when we're pulling in all of this other work that everybody else has been doing. And this is when the actual the decision support tools come to life. And in developing, we're regularly testing. And with each development phase, usually it's the development team that's doing testing, and we're trying to catch implementation issues. And then as the tool is developed enough, we want to start to have end users participate in this for beta testing, as Victoria had talked about on the species selectors and beta testing. And so end users could be anybody from other members of PSA to some of the students in the cross-country course that's being designed right now. And the idea in these later testing phases is that we can catch design issues or data issues. And a lot of the design issues and data issues are actually relatively easy to fix. I mean, it still takes quite a bit of time, but what is most important here is this loop back on the far left, which is catching the data framing or inclusion issues, which could really cause us to have to reassess our data dictionary or our decision flow model, which then allows us to, or requires us to kind of go all the way back through the model. And this might seem like a problem, but this is actually an asset to the development model for decision support tools, because it really allows us to accommodate all the new research that will be coming into the the model, into our work as we continue with our work in the on-site trials and whatnot. And so, yeah, it's imperative that we design to accommodate for this iterative model, or something like that, especially we need to support the ability to go back and modify or fine tune the data dictionaries that structure our data in the design flow. So that's like the major takeaway here, and kind of the way to go about it. So that's all I've got. And Stephen, do you have anything to add to that?
Thank you. That was fantastic, Juliet. Thank you so much for giving some of the framing about kind of how we're approaching a lot of these tools and how they're structured and the evolution. So this was really, really good. And I think for those in the room, what many of you have seen before with our network is this expert-based tools like the seeding species selection tool that the Midwest Cover Crop Council developed a while ago, and that the Northeast has been actively involved in. And so many of you have some exposure or experience with that process, at least at some level. And so what we were hoping to also do now is give you kind of a use case here that's more coming out of our IoT systems and the destructive samples across the network. But I hope you can see now how a lot of these kind of pieces come together and what some of our workflow is. So let me now transition and give Aurelie a chance to circle back to what she presented on yesterday and give an example of this process, right? And again, remember that some things have the luxury of going through the entire workflow process that Juliet described, right? Because we're starting collectively and having kind of information scientists like her working at the table at the formation of a model and a tool in that process. But in other cases, we're taking an existing tool and regionalizing it, or taking an existing model and regionalizing it. So just be aware that that some of our process and some of these workflows have to obviously also have to adjust based on where we enter that process with a given model or tool. So with that, Aurelie.
Thank you. Hi. So thank you so much, Juliet, for the presentation. It was very informative. So like Stephen said, we have been conducting the analysis, and we are just starting to try to convert the result of our model into a decision support tool. And I wanted to just take a few minutes to walk you through kind of like the thought process of how we are going from the modeling to the DST. So like Juliet said earlier, the first thing that we need to do is to kind of define like the problem and the objective of the tool. So we pretty much have three possible like type of objectives. So this is like a tool can have like a learning objective. For example, we might want to educate growers about the impact of cover crops on soil, water, and nitrogen dynamics. We might have more like a decision-making tool where we want to provide growers with nitrogen fertilizer rates or irrigation recommendation according, to their local management condition and management strategies, growing condition and management strategies. And we can also have some an objective that would be more about informing technologies that the grower might have. So it could be, for example, using the result from the remote sensing work and the geospatial work and the models to generate prescription maps that growers can input into variable rate technology. Next. So when we have developed the objective, then we need to think about how we are going to meet this objective. So the process we have been using for the water DST is kind of a backward process. So we define the objective and then the output, and then we kind of try to build up to the information we need to provide the grower. So the first, so step 2 basically is define the model output. So for example, we might want to show, and like Juliet said, it needs something to be simple, easy to understand, and informative to the audience we are targeting. So for the water and nitrogen tool, we might think about providing growers with the amount of nitrogen released by decomposing cover crop biomass, or the current crop water status. So is the crop stressed or is it not stressed? So thinking about things like that. Next. Then we might think about the information that we will need to gather from the growers to be able to produce that output. So for example, we might want to ask growers about the amount of nitrogen, of a cover crop residue, sorry, that like that are in their field, or like cover crop termination date, cover crop termination method, cash crop planting date, etc. Like their location, so we can gather, weather information and soil information. And next. And when we know where we want to go at and what we need to get there, then we need to think about the model we are going to use to be able to make that transition. So that can be, the result from our statistical model, our machine learning model, or process-based model. Each model having their own strengths and limitations. We need to choose, the ones that work best. Next. So when we talk about development of a decision support tool, we kind of have we're talking about two different things that kind of go together. So like you will have like kind of like the front end, which is going to be the user interface and the design. So in the design of the tool, which is kind of represented with like my tablet, the actual like design of the plot or the colors that you are using, or the menus that you have to get this information you want. And behind that, you will have what we call the back end of the tool, which is basically all the computing tasks that are occurring behind the user interface to convert the input into the output. So that includes data transfer and modeling and communication with the server. So those two are linked together, but also very independent. So the interface, like the front end is kind of like the, like the shape of your car, and the back end is the motor running it. So if you build like a front end that's flexible enough to meet, your objective, then the models and can change in the back, and you can, improve your algorithm over time. I don't know if that makes sense. Stephen, feel free to jump in anytime. So next slide. So, when I think about building a DST, and since I have been, going through the whole process from like the data collection, the data management, the modeling to the DST, I kind of see it as boxes that you can put inside bigger boxes. So, it's starting with like statistical and process-based model. Next. And then we're gonna, so we build this model, and then we are gonna concatenarize those models into like a backend platform that we have been like calling APIs. So for the ones that are not familiar with what that is, it's basically an intermediate between the model and the tool, where you associate an HTTP link to your model, so that you don't have to look at the code anymore. You can just query that code and directly like gather the output. Next. So then that API, you can use it, and query it on the backend to drive the first version of your DST. So typically, like for the water, we're gonna start with something simple, and we're gonna start building, more complicated functionality. So initially, we might get nitrogen recommendation for like one location, or we might get, for like corn only. And then next. And then, we might be able to start integrating soybean and cotton, and we might start thinking about geospatial functionality and kind of build on that. So it's kind of a growing process that starts from the model, to meet like our overall objective. And I think that was the last slide. And I think that makes sense, like Stephen.
Yes,
so I don't know
that's
if like,
perfect. That was great. That was great. Thank you so much, Aurelie. I think that this really helped kind of highlight, some of our various approaches on some of our various tools, and how we're starting, for example, with this water tool. And I really liked how you emphasized that, it's not so much, mission creep on a tool. It's just as you get into a tool and you have a preconceived notion of the inputs and the outputs and how it's going to be used, whether it's educational purposes, whether it's for researchers, or whether it's, really decision support or driving a precision technology. As you evolve over time, you see opportunities to expand the offerings of a tool. And so that's, what kind of, I think, Aurelie really highlighted nicely, as well as Juliet. So anyway, thank you. So now Resham is going to describe a slightly different process, which is where we are coming into a tool that has, a lot of momentum, right? The University of Georgia under Miguel Cabrera and several others, including Rick, led the effort on building a model and developing an interface around that to serve farmers in Georgia. And now we've been working closely with that lab for the last 4 or 5 years now to regionalize that tool and make it a national tool. And so Resham has really been the linchpin between these efforts, because he basically spent his last 4 years in his PhD working closely across this space to do that with the PSA team and Miguel. So Resham is going to highlight that dynamic a little bit.
Thank you, Stephen. So far, like Juliet and Aurelie already mentioned that the design process of the whole DST, right? What involves to the successful design of the DST and then the well adoption of those DSTs. And here is a good example of the DSTs that has been designed by a team from University of Georgia, especially like Dr. Miguel Cabrera and Rick. So they designed this DST to determine the availability of nitrogen during the decomposition of cover crop residues in the subsequent cash crop season. And this is the DST which I showed in yesterday's presentation, the model. So the in the back end, the model upon which this DST was built is the series model, which requires a very basic inputs such as the cover crop data, the weather data, and the soil data. And since the University of Georgia has a wide distributed network of weather stations, right now this tool uses the weather information from the weather network that the University of Georgia has. And to successfully design the DST, we wanted to understand what are the user groups, so to whom we are targeting and what are their needs, right? And it needs to be very simple as well as easy to implement. Next slide, please. So as you can see in the first on the left, you can see Georgia, right? So this tool is initially calibrated and validated and has been successfully implemented throughout the Georgia. So farmers from Georgia, especially organic farmers, were heavily using this tool to predict the amount of nitrogen available in their organic farming systems in cover crops. So especially in Georgia, what farmers do is like this: sample a cover crop biomass from their field, send it to the lab, where the lab analyzes certain quantity and quality variables for that cover crop biomass and gives the output to the farmers in terms of the amount as well as the timing of nitrogen available from the cover crop residues to their subsequent cash crop season. Now, how can you convert this tool that is well established in Georgia and expand it not only to our partnering networks, not only in the Mid-Atlantic or the Southeastern and the Midwest, but across the whole US nation? And to do that, first thing is to parameterize the model upon which these DSTs are built on. So by that mean, what I mean by that is that the model upon which these DSTs are built need to be trained to capture all kinds of soil, climate, as well as management interaction effect. Because across the landscape, we have this different soil type, different climatic regions, as well as farmers really differs with respect to their management practices. So we need to totally capture what drives the model performance, what are the various sensitive information that we do not need to miss in order to properly capture the functionality of the DSTs. The second thing is we need to standardize the data sources. For example, if you take the DST I'm discussing here, at the University of Georgia, they have this weather station. So they take this data from the weather station. But for Maryland, if you consider Maryland, we do not have that expanded network of weather stations here. And also using different weather sources might break the DSTs or might break the models upon which these DSTs are built. So to make sure these DSTs functions and are widely applicable across the nation, we need to have a standard source of data. And for that, we built the weather API, which takes weather information from nationally available or publicly available weather data products, such as NLDS and YAMRMS. And we need to make sure that DSTs need to be well adapted across farmers. And since right now, these DSTs provide a point-based estimate of the nitrogen available for a particular farm at the farm level. And is that sufficient for farmers? That is a big question, right? The farmers may want to know what is the special map, or to what extent the cover crop is performing in their particular farm, and what is the amount of nitrogen that is available across the whole farm level, not only at a point level, but as a special extent. And to do that, we need to make sure these DSTs are linked with the remote sensing images, so they can provide the special context of the decomposition as well as the nitrogen availability. And the other thing is that I want to mention here is that there's a lot of room, even once these DSTs are highly developed and highly calibrated, there is a lot of room with the various groups within the PSA. For example, the remote sensing, even we can test these DSTs that we are building over here with the Common Experiment 1 group, and also we can train the next generation of scientists through education and outreach through the application of DSTs through education module. And the other thing is that with regard to social science team, what we can do is that we can have questions such as what drives the adoption of DST with respect to farmers? What are the typical things that drives the performance or that drives the adoption of DSTs among the farmers across the nation? So that's all I have. Thank you.